Here's where we left off yesterday. I fixed my sign issue. As I said on the first day of class, enthalpy comes from a Greek word that sounds a little similar to enthalpy. It means to heat. And we defined enthalpy as internal energy plus the product of pressure and volume. When the system changes at constant pressure, the change in enthalpy is this expression right here. Change in internal energy plus PV, and then we can distribute the delta through. And here's our first law of thermodynamics. Change in internal energy is equal to heat plus work, and work is equal to minus the pressure times the change in volume. We substitute that into the expression here, and we get something that looks like this. And then if pressure is constant, well, after this algebraic magic, we get this when pressure is constant. And so I told you about this first term, or this term, first day of class. And I also explained the one of the online homework problems when they tell you a change in enthalpy, and you can substitute that in for Q. So when I was a student, I'm like, oh, I got to understand this derivation. Now, this derivation is for your information, so you know where it came from. Down here is more of the things you need to understand as a thermochemistry student. And this is probably maybe the third or fourth time we've gone over this. Delta H is positive for an endothermic reaction, and it's negative for an exothermic reaction. And so on the quiz and on that problem, you got to be able to figure out the signs. So this should remind you of the ice cube in a drink. Heat is being absorbed to melt the ice. And so heat is a reactant. And the change in enthalpy is positive, and we say Q is positive. So another interesting thing might be perspiration. That's what ladies do. They perspire. Guys sweat like pigs. And so how does that cool your body down? We can draw a thermochemical reaction that says liquid water going to gaseous water, and the gas has more kinetic energy, balanced energy. We got to put heat as a reactant. So that's how your body cools itself. Liquid water turning to gaseous water is an endothermic process. Now, if you get a quiz question and it says, what's the sign of Q when you make pasta? And you put a pot of water on the stove and make it boil. You want to think of the heat that the stove is adding as a reactant. When heat leaves the system, we have a negative delta H. Change in enthalpy will have a negative value. Q is negative. And it's just the opposite of boiling water on the stove to make pasta. If your car has ever overheated and you open up the hood, hopefully your radiator cap says, warning, do not try and open this thing hot. Why is that?
Because it's boiling water.
Well, yeah, you can get a steam burn. So when it's hot, when gaseous water condenses into liquid, that heat gets released, and the surroundings is your hand or whatever gets into the steam. Enthalpy of reactions, something we measure and tabulate. The change in enthalpy, delta H, is the enthalpy of the products minus the reactants. Once again, we don't look up single H values. We look at delta H. And we can plot enthalpy on here. It's very similar to plotting change in internal energy. So here is methane, CH4, and O2 gas. So you might have a natural gas furnace at home that heats your house. How does it? At least I get a gas bill, and in the February it can be like $200. What am I paying for? Well, the natural gas comes into my house and gets combusted, combined with oxygen. There's a pilot light burner, and that releases 890 kilojoules per mole. For 1 mole of methane, per 2 mole of waters that get formed in this reaction, per 2 moles of oxygen. So we kind of went over that concept with our problem yesterday. And here are our products. Now what I like about this is this arrow is going from reactants to products. Well, we'll learn that we can write a thermochemical equation in the reverse order, and it just changes the sign, not the magnitude. We'd like to figure out what to do with carbon dioxide. And if we have this much energy, we could take carbon dioxide and water and change it back into methane. But it would take this much energy. So this quantity, delta H, is called the enthalpy of reaction, or heat of reaction. So here's a thermochemical equation where hydrogen gas and oxygen turns into water and releases this much heat. So these chemical species here are at a higher energy state, potential energy due to the nature of their bonds. Water's kind of at a low energy state. How do I know water's at a low energy state? 2/3 of the earth is covered with water. It's kind of the bottom of the hill. So here is an image of a famous thing. Does anybody know what this is depicting?
Isn't that Hindenburg?
Yeah, that's the Hindenburg, and it was just a non-copyrighted image I found. And what was the Hindenburg filled with? Hydrogen. It's easy to make hydrogen a little cheaper than helium. Helium's kind of hard to get a hold of.
Hydrogen's explosive.
Right, it's very flammable. So a bunch of people died. I don't know if it's static electricity got it going once it gets going. So every now and then somebody in the community says, why don't we make cars that just run on water? Isn't water just hydrogen and oxygen? And I'm like,
You saw what happened last time we tried doing this.
no, well, water is at the bottom of the energy hill. If we have hydrogen and oxygen, we could have a car that could burn hydrogen and oxygen, and the product would be water, and that's very non-polluting versus like carbon dioxide and other things. But you can't burn, it's hard to get any energy out of water. I could put 483.6 kilojoules into water, 2 moles of water, and turn it into 2 moles of hydrogen gas and oxygen gas. And then we actually want green hydrogen. Right now, the cheapest way to get hydrogen is from petroleum products, from oil out of the ground and reacted in a certain way, and you can make hydrogen. And it probably produces CO2 in the process. What is an extensive property? Asked you this yesterday. We compared and contrasted it to an intensive property like color or density. I can look at one snowflake and tell you it's white. I can look at a big glacier and tell you it's white. Color is intensive, doesn't matter how much is there. So an intensive property matters how much you got. Like mass or volume is an extensive property. So here is our Hindenburg reaction, hydrogen and oxygen combining to form water. And here's how it's balanced. So everything in your textbook, it's going to say per mole. I'm kind of an old school person. If it's not written, it's assumed to be there. So notice down here, I've written the reaction in the opposite direction. And we have the same magnitude, but a different sign. And that tells us this much energy over here as a reactant is going to be required to drive this to products. Over here, this much energy is a product. So when this reaction goes, it gives off this much heat. Since it gives off this much heat, the system is being lowered by this amount of energy.
So by adding that amount of energy back in, we'll undo it, basically.
I should have had a couple arrows there. So some guidelines for working and dealing with thermochemical equations. Here's where I fall kind of short. I never like writing the chemical states, but it can matter quite a bit. See here, water is in the gaseous form. All of our reactants are gases. Here's our products that are gases. Now if I write this as liquid form, down here, it changes. Alright, I wanted to fix that typo. So notice, this gives off even more heat than the above reaction, because gaseous water has more kinetic energy, and get it down into a liquid, even more heat's going to be product, more exothermic. So this reaction is exothermic to begin with. It's a little less exothermic than this one down here by 90 kilojoules, and the difference is water being in the liquid state here and the gas state up here. So we can manipulate a thermochemical equation algebraically, like we can multiply by an integer. And it's kind of like algebra. What we do to one side of the equal sign, we do to the other. And a chemical arrow is just like an equal sign. And so the difference here looks like I've multiplied by 2. There was a 1 here, now it becomes a 2. 2 times 2 is 4. 2 times 1 is 2. 2 times 2 is 4. And so what's the difference here? Yes, double. So since I'm going to take this thing and times everything by 2, I got to times this one too. So 2 times negative 802.4 is 1604.8. And if I reverse this the way I write, it's just like in algebra, you would subtract all these things from one side and have to subtract them from the other side, or plus them, and they move around. It's the same thing up here. Get this to go away from this side of the equation, almost like you put a plus sign here. We would have to add 802.4 kilojoules to this side. Then it shows up over here. It shows up over here due to the positive sign. But if we think about heat being a reactant or a product and which side we write it on, I always like to do that, and then that helps us understand these signs. So the change in enthalpy depends on the state of the products and the state of the reactants. Got to pay attention to the solid, liquid, gas. And we learned the other day, enthalpy is a state function. What does that mean? State function depends on only the initial and final state of a system. Alright, here's some fun things to think about. So how does a chemist go and learn these numbers and study things? Well, all matter has a physical property. It's kind of like density. Density is a physical property in that I can measure it and observe it without altering what it is I'm measuring. Just to contrast that with a chemical property, which the only way you observe a chemical property is a chemical change, and then you don't have what you were started out with. So chemists use this thing called calorimetry, where we can measure heat flow, normally by a change in temperature and knowing some other things. So the first thing we're going to look at is heat capacity. That's the amount of energy required to raise the temperature of an object by 1 degree C. So that's kind of general. Like my body has a heat capacity, this mug has a heat capacity. But if we specify a little more detail, we use this word called specific heat. Specific heat is the heat capacity of 1 gram of substance. The amount of energy required to raise the temperature of 1 gram by 1 degree C. So I told you that water has a heat capacity, a specific heat of 1. When I talked about what is a calorie is the amount of heat required to raise 1 gram by 1 degree Celsius. And 1 calorie equals 4.184 joules. So if I have 1 gram of water and it's at 14.5 degrees Celsius, and I add 4.184 joules of heat, it's going to cause the temperature to increase by 1 degree Celsius. So the key to most of these problems is units, and I like to break it down like this. Sometimes I draw little boxes around these. Specific heat is the heat transferred per mass per temperature change. And so you might see an equation that looks more like this in your book. Here's our Q, which represents heat. Could be calories. Most of the time it's joules. And here is mass. And here is the temperature change. So in the lab, it's easy to weigh something. Know its temperature. Do something else and measure a temperature change and possibly calculate heat. So here's the specific heat value for water, 4.184 joules per gram per degree C. And when you go to do a problem, that per degree C in gram, put a big line and make it look like what we call the railroad track method of solving chemistry problems. See right here, there's that big division line, but drawn in such a way students miss it. So I kind of like to think about it like maybe when you calculate what type of mileage you're getting in your vehicle. You drive 300 miles, and it took 10 gallons, so you go 300 divided by 10, and you say, oh, I'm getting 30 miles per gallon, even though the number of gallons was some multiple amount. Same thing here. The temperature change is something you measure, like 10 degrees, 5.6 degrees, whatever. So when you divide by a delta T, a temperature change, you get a unit of just a degree C in the bottom. Same thing with grams. Next week when you go into the lab, you're going to weigh a chunk of metal, and it might weigh 65.7 grams. And then you might measure a temperature change of 83. And somehow you're going to figure out the heat. And when you divide the mass and temperature change into heat, these come out as coefficients of 1 that we don't write. So here we got iron specific heat, 0.45 joules per gram per degree C. So for a given amount of heat absorbed, let's say we have equal masses of water and iron, which gets hotter, iron or water?
Isn't it going to be water?
Let me back up a little bit. Say we have 100 grams of each, iron and water, and we each let it absorb, 100 kilojoules. Which is going to have the larger temperature change?
Isn't it going to be the iron because it requires less energy?
There you go, absolutely. Yeah, so we say water is a great coolant because it takes a lot of joules to change its temperature by 1 degree C. So if you have an iron engine block, I think most of them are going to aluminum. The old engines had iron engine blocks. Aluminum's not going to be a whole lot better. You can see it's a little bit better. But yeah, you got to add a lot of heat. Notice this is a 10 times difference, roughly. Here's 4, here's 0.4. So when you add some heat to iron, its temperature change is going to change a lot quicker or greater than adding the same amount of heat to the same mass of water. We've looked at heat capacity. We've looked at specific heat. Now here's molar heat capacity, which is the amount of energy required to raise the temp of 1 mole by 1 degree C. So here for water, if I multiply this by 18.02 grams per mole, the grams would cancel out and I'd get moles in the bottom. And that's what molar heat capacity. So here's some metals. Here's water. All right, here we go. How much heat is required to raise the temperature of 3.8 kilograms of water by 25 degrees Celsius? All right, there's our specific heat of water. Fix that up. So, if we forget our specific heat formula, it's all built into our units. So I look at that and I see that, well, I can probably start out. And here I tell students, make that per thing look like a real fraction. And now I have something that might look like a unit factor to do conversions. All right, and then I see a unit of mass. So I'm going to multiply by 3.8 kilograms. And then I'm going to say to myself, thank you, I can't cancel these. So I'm going to put kilogram and gram like this. And then I'm going to say kilo means 10 to the third. So I want to be sure and put 1 there and 10 to the third up there, which is 1,000 grams. I need to multiply now by, well, now my kilograms are going to go away. Grams are going to go away. How do I get rid of degrees C? All right, well, this one's going to be fairly straightforward. And now all my units are going to cancel like they're supposed to. Must have been a fat finger error.
Joules, and then if you divide that by 1,000, then that would be kilojoules. Is that right?
Right. More significant digits than I need. I want to go on to something better. All right, when 28 grams of water at 10 degrees Celsius absorbs 2,000 joules of heat, what temperature will the water... So once again, I want to look at these units, and students always want to make this more complicated by saying, well, delta T is final minus initial. And we don't want to go there. That just makes things messy. What we want to do...
Can't we just use the formula to get the joules and then add the 2,000?
We want to solve for a temperature change. And then add delta T to T initial. That's going to be the simplest way to do this. All right, so here's my change in temperature. So what that means is I'm going to start with my specific heat down in the basement. So now I have that unit of degrees C up top. And once I get going there, everything else is just make all my units cancel. So I'm going to put joules up top. They cancel there. Now I need to get rid of grams. Put that down there, so now grams goes away. The only unit that remains is my degrees C, and that represents a temperature change. Hopefully I won't make the mistake I just did. So I start out with my calculator going 2,000 divide 1.184 divide 28. I got more digits of that in my calculator, and so then I'm going to take that, and it says at 10 degrees, and then I'm going to add the temperature change. This to 27.1, and probably look at this and figure out delta T is 27 minus 10, and we get our 17.07 there. And let's see what this gives us. 4.184 times 28 times 17.07. And I did a little rounding there. That's pretty close to our 2,000 joules. So we can be pretty sure we worked the problem correctly. All right, that's enough to digest for today. We'll cover more ground tomorrow, and then we'll have our weekly quiz. Any questions? All right, have a good rest of your day.